This is example 3 on page 147, and it's about hypothesis testing. So far this semester we've developed methods for analyzing data, so we're going to move on and set up hypotheses to test our theories and claims. So this is an example that I had with an English professor at LMC. So last week, Ms. Caldwell told me that she believes Umoja scholars see academic counselors more than other non-Umoja students. How can we test this claim to see if it's true? So we set up the following study to test the claim. So our question here is, are Umoja scholars more likely than non-Umoja students to see an academic counselor? So our two hypotheses are going to examine this claim. So our first hypothesis, the null hypothesis, we use H sub 0 to indicate that hypothesis. So the null hypothesis says the proportion of Umoja scholars who receive academic counseling is equal to the proportion of non-Umoja students who receive academic counseling. So remember, the null hypothesis is no change, so that's why this is equal. It's saying there's no difference between Umoja scholars and non-Umoja scholars. Down here, H sub A is the alternative hypothesis. So you can remember A for hypothesis, A for alternative hypothesis. Sometimes this is written H sub 1, so you may see that occasionally in some of the examples. And the alternative hypothesis is saying the proportion of Umoja scholars who receive academic counseling is greater than the proportion of non-Umoja students who receive academic counseling. So question A is asking us, what is the claim? So we want to go back to see what Ms. Caldwell was saying in her claim. And it tells us Ms. Caldwell believes Umoja scholars see academic counselors more than other non-Umoja students. So that's the claim that we're investigating. So the claim that we are investigating is that Umoja scholars may be more likely to see academic counselors than other non-Umoja scholar students. So before we go about collecting data, we have to set up our hypotheses and then figure out how we're going to test them. So the null hypothesis is the first statement, H sub 0. So we'll say H sub 0 is the null hypothesis because we are stating no change. In the null hypothesis, we assume that the proportion of Umoja scholars who receive academic counseling is equal to the proportion of non-Umoja scholar students who receive academic counseling. So here, this is our assumption of no change or no difference. So we assume that there is no change or no difference. Now H sub A is the alternative hypothesis. So down here in part C we can explain that. And then I'm going to make a note that H sub A is sometimes written as H1. The null hypothesis has a 0 to indicate that it's no change. So sometimes the alternative has a H sub 1 depending on which text you're looking at. So this statement says that the parameter is greater than the non-Umoja student's value that we assumed was equal in the null hypothesis. And the parameter that we are testing is the proportion of students who see counselors. And we should say who see academic counselors, because there's other types of counseling. So on the graphing calculator, because this is greater than, when you set up your hypothesis test, you will choose the greater than inequality symbol. So if you go to page 148, here's some general observations about null and alternative hypotheses that'll be helpful. So the first bullet says that the hypotheses are competing claims about the parameter or about the comparison of the parameters. So they have to have different claims that they're making in the two hypotheses. Both hypotheses are statements about the same population parameter or the same two population parameters. So they can't be statements about different populations or we wouldn't have a way to compare. The null hypothesis always contains the equal sign because you can remember the null hypothesis means no change. The alternative hypothesis is always an inequality statement. So it's always going to be less than, greater than, or have the not equal to symbol. In a statistical investigation, we determine the research question and the hypotheses before we go collect the data. So the steps in statistics are first determining your research questions, then your hypothesis, then collecting the data, then analyzing the data. So there are 4 steps to the hypothesis testing process. So step 1 is to determine the hypotheses. And so the hypotheses come from the research question or the claim that someone is making. Step 2 is collect the data. So ideally we have a random sample from the population. And the data would come from this random sample. And then we can calculate the statistic. And the statistic can be either a mean, which is an average, if you've got all quantitative data, or a proportion, like we have here, that goes with qualitative data. So maybe I'll put a note here that the mean goes with quantitative data. And we'll put that note under the mean. And then qualitative data, or I'm sorry, we use the word categorical data for the proportion. And so once we calculate the statistic, whether it's a mean for quantitative data or the proportion for categorical data, we then can summarize the data. Step 3 is to assess the evidence. So we always start by assuming the null hypothesis is true. So we assume that there's no change, and then we have to prove whether or not there is a change. So we ask the question, could the data come from the population described by the null hypothesis? And then we use a mathematical model to examine the results from the random samples selected from the population described by the null hypothesis. And again, remember we use random samples because it's very difficult to study a whole population. So we always have to pick a sample out of the population. 99% of the time we want data. Then we figure out if results similar to the data are likely or unlikely. And note that the wording likely or unlikely implies that this step requires some sort of probability calculation. So this is where our confidence intervals and probability come into play. Step 4 is about stating a conclusion. So we use what we find in the previous step and we make a decision. This step requires us to think in the following way. And remember that we assume that the null hypothesis is true, and then there are two possible outcomes. One possibility is that the results similar to the actual sample are extremely unlikely. So this means that the data do not fit in with the results from random samples selected from the population described by the null hypothesis. In this case, it's unlikely that the data come from the population, so we view this as strong evidence against the null hypothesis. So this is when the results tell us the actual sample is extremely unlikely. So in this case, we reject the null hypothesis in favor of the alternative hypothesis. So we do this when we get a really low probability that the results are likely. The other possibility that results is that results similar to the actual sample are fairly likely, so that they're not unusual. So this means that the data fit in with typical results from random samples selected from the population that the null hypothesis describes. In this case, we do not have evidence against the null hypothesis, so we cannot reject it in favor of the alternative hypothesis. So this means that the probability comes out high. So we can put some notes here. Let's see if this will let me mark it up. So the first possibility is low probability of the null hypothesis. And this second possibility is high probability of the null hypothesis. Okay, so if it's low probability, we say we reject the null hypothesis. If it's high probability, we cannot reject the null hypothesis. So here in example 4, we see that hypothesis tests can be what we call one- or two-sided. So depending on how the alternative hypothesis is written, or how we're testing, or which alternative hypothesis we're testing, there are choices for the hypothesis test results. So the hypothesis test could have a left-tailed p-value. So that looks like this first example where the p-value is off to one side. And so this is when we say that the proportion is less than what we're assuming for the null. So this p sub 0 is what we're assuming the proportion is for the null. And what one possible result could be that the proportion is actually less than the null. The second option would be what we call a right-tailed p-value, which is up here on the right side of the graph. And that's where the proportion is greater than the null proportion. The third option is a two-tailed p-value. And that's where we only know that the probability is not equal to the null probability, but we don't know if it's below the graph, or below the mean, or above the mean or the proportion. So remember, the middle, if it's quantitative data, it'll be a mean in here. If it's categorical data like we're looking at now, this would be the proportion. So for each of the following scenarios, we're going to write the null and alternative hypotheses and explain if the model will have a left, right, or two-tailed p-value. So in a taste test, participants are comparing Pepsi to another cola drink and rating the sweetness on a scale from 1 to 10. Scientists planning the study claim that the other cola is more sweet than Pepsi. So we always start with our null hypothesis. So our null hypothesis is going to be no change. So we can say that the sweetness rating of the other cola is equal to the sweetness rating of Pepsi. Now, when I wrote my hypothesis, I chose to put the other cola first. You could have put Pepsi first, and you'd see how, depending on which one you put first, that changes the direction of the inequality. So now my alternative hypothesis, I'm going to say the sweetness rating of the other cola is greater than the sweetness rating of Pepsi. And so my inequality is going to be greater than, because I put the sweetness cola first, right? And the scientists are claiming that the sweetness cola is more sweet than Pepsi. So we want to think about what type of p-value will this be. So because the claim is greater than, this will be a right tail p-value. And remember, the p-value is telling us the probability that the null hypothesis is true. Question B asks, does the job satisfaction of assembly workers differ when their work is machine-paced with a timer rather than self-paced? Workers are assigned to an assembly line moving at a fixed pace or a self-paced setting. All subjects work in both settings in random order. After 2 weeks in each work setting, the workers take a test of job satisfaction. The response is a proportion of satisfaction scores in each setting. So let's go ahead and write our hypotheses. The null hypothesis H sub 0 is the proportion of satisfaction scores for fixed pace assembly is equal to, right, because remember it's a null hypothesis, the proportion for self-paced assembly. Okay, and then our alternative hypothesis, H sub A, is going to say the proportion of satisfaction scores for fixed pace assembly is different from the proportion for self-paced assembly. And so this isn't saying greater than or less than, it's saying different. So this is a two-tailed hypothesis test because we don't know if the p-value is greater than or less than the proportion. So that makes sense? Because it says different and not greater than or less than, we would use the not equal sign and we wouldn't know whether it was a greater than or less than, and we wouldn't know whether it was a left-tailed or a right-tailed p-value. Does that make sense? Okay. So if we go look at page 150, example 5 is about types of errors. So there's two types of errors in hypothesis testing. We call them the false negative and the false positive. And this diagram explains the types of errors possible. So if we look at the first column, this is saying the null hypothesis is true. So if the null hypothesis is true, there are two possible results. So the first result is that we would reject the null hypothesis. Well, that would be an error because we know the null hypothesis is actually true. So we call this a type 1 error or a false positive. The second option is to keep the null hypothesis, and in this case the null hypothesis is true, so that would be the correct conclusion. Okay, what if the alternative hypothesis were true? Then the first option, to reject the null hypothesis, would be the correct conclusion because our alternative is true. The second possibility is that the alternative hypothesis is true, but we keep the null hypothesis. So this is another error because it's not correct. And so this is categorized as a false negative or a type 2 error. So let's look at this example. So a company markets a computerized medical diagnostic program used to evaluate thousands of people. The program scans the results of routine medical tests, so pulse rate, blood tests, etc., and refers the case to a doctor if there is evidence of a medical problem. Question A asks, what are the two hypotheses and the two types of error that the computer program can make? Describe the two types of error in terms of false positive and false negative. So we've got to explain, first of all, the two hypotheses, and then we'll look at the possible errors. So the null hypothesis, H sub 0, is that there are no differences, or there is no difference in the medical tests. So, in other words, this would be a healthy patient. The alternative hypothesis is that there is a difference in the medical tests. So, this would be, in other words, evidence of a problem. So, a type 1 error would be that the test reports positive when the patient is healthy. So we would call this a false positive because it's saying the patient has some evidence of a problem when they don't really. The type 2 error would be the opposite, that the test reports negative when there is evidence of a problem. So we call this a false negative. So medical tests are a good example of thinking about false positives and false negatives. Other good examples would be pregnancy tests, or if you're checking a battery, right, and it tells you whether the battery is still good or not, right? It could tell you incorrectly. So this computerized medical diagnostic program that we're examining in this example can be adjusted to decrease one error probability, type 1 or type 2, at the cost of increasing the other error probability. So if you decrease type 1, you increase type 2, and vice versa. So which error probability would you choose to make smaller and why? So I said this is an opinion question, but I'm going to let you know my opinion. So let's think it through. So a type 1 error, false positive, would cause concern and worry because the patient thinks he or she has evidence of a medical problem, but is really healthy. Okay, a type 2 error, which we call the false negative, would not alert the patient to existing health problems. Okay, so there's a little bit of opinion in the next part, but I think that the false negative and the false negative is the type 2 error is more dangerous, right? Because the person might not know about health problems going on. So I will make the type 2 error smaller. Okay, next go work on the group problems and remember to check in on the group forum.